This video will focus on some of the intro concepts of dissolving. It's to take the place of class if you had to miss today. So we talked about the two steps that it takes to dissolve anything the other day. Those two steps are dissociation and hydration. The fact that the compound, whether it's polar compound or ionic compound, falls apart into its tiniest pieces it can, step one. And then step two, those pieces are essentially supported and hydrated by whatever the solvent is. In this case, usually water, but it doesn't matter. If we take these concepts and we actually relate it to thermochem, our last unit, we can see where delta H of solution came from. So delta H of solution is the amount of energy either absorbed or released during this process of dissolving. And since during the process of dissolving, you are actually breaking up one set of forces of attraction, whether they're an ionic attraction or a polar IMF attraction, and then new ones are being formed between the solvent and whatever the solute is. And since there are bonds being broken and bonds being formed, essentially we can have a change in energy. So in order to understand the whole idea of energy change during dissolving, we have a picture again of dissociation and hydration. So during the dissociation process right here, we're going from having an ionic attraction between sodium chloride to breaking that attraction. And anytime you break a bond, you have to put energy in. So the first step, dissociation step, will always require an input of energy to make it occur. Then as we hydrate, so remember these two steps are happening pretty much simultaneously. So then as we hydrate, we're making these new forces of attraction between the ion and in this case, the dipole moment on water. And anytime we make a new attraction, we release energy. So during the process of dissolving, if our substance releases energy, like in the end, after I dissolve, the water around it gets hotter. The reason that would happen is because I'm releasing more energy in this process than it took to break them, right? Because the amount of enthalpy, the delta H, is always the product and the reactant together, a comparison of the two. So if instead when I dissolve it, it gets colder, that means it took more energy to break it apart than I released when I made a new attraction. So essentially when you dissolve something, you can see there are forces of attraction being broken and formed. It's not really a bond necessarily. There's no covalent bonds being broken. The ionic attraction is separating and getting replaced by a new attraction, but essentially you're going to find the delta H's or the energy associated is less than if you were to break a normal covalent bond because these are more IMFs. These are just forces of attraction and they're not necessarily full associations. So a solution is always a solvent with a solute, something that is dissolving something else. So the solvent is the thing that is dissolving the solute. Most commonly in our heads, we think of that water with salt example or water with sugar example, but there are lots of different solutions and solutions you even encounter. Okay? Air around you is considered a solution. It's a nonpolar solution, so in terms of identifying like what's the solvent and what's the solute, we usually just go with the solvent being the more massive or the one with the most amount. So like nitrogen in this case would probably be the solvent and the solute would be all the other gases. Another solution that we have around us sometimes is humid air. So in that case, the solvent is a gas and the solute is just that water. There's a very small amount of water that gets dissolved into the gases. Okay. Another solution that's not a liquid and a solid are pop. Okay. That's a liquid solvent, water, that's dissolving a gas. Okay. And in that case, that gas is nonpolar usually, and we'll take some time on a different day to talk about how a polar solution can dissolve a nonpolar thing in that way, what conditions allow that, but that's another solution you come in contact with that's not a liquid with a solid. Acids, any acid like vinegar or the acid in your stomach, that's a liquid with liquid. And then there's the class of liquid with solid. There's also solid solutions, which is strange to think about. We already talked about our alloys. Those are solid solutions. So those are two solids mixing together to make a solution. So any alloy would be considered a solution. And we even have some solid solvents with liquid solutes that are essentially alloys, but one of the metals was a liquid to begin with. So there's lots of different types of solutions. Solutions are not determined by state of matter. Any state of matter can mix with any other state of matter to potentially make a solution. It's all about the process. Did I go through dissociation hydration? Are the particles small? Do I have a solvent and a solute? Things like that. So be aware of that. We are not limited by a liquid solvent with a solid solute. Now, in our lives, it is convenient if we can get nonpolar things to dissolve into polar things. And we know the rule is like dissolves like, polar dissolves polar, nonpolar dissolves nonpolar. But the problem is, in terms of, let's say, our bodies or our food, we have lots of oils in an environment that is aqueous, right? So if you get oil on your skin and then try to wash it off in the shower, well, that oil isn't going to dissolve into the water. Or if you're trying to clean off like a baking pan, or for food, if you're trying to get oil to mix in with like a water-based food, they tend to separate or not to mix. So the use of something called an emulsifier or a surfactant. So a surfactant is essentially the fancy term for soap. Emulsifier is what soap is called when it's used for food instead. So it's an edible type soap. And surfactants and emulsifiers are used in order to allow nonpolar things to dissolve into polar things. So you'll see in this picture, that picture of a surfactant with the red head and the little gray tail. Surfactants have a hydrophilic head, so that means water-loving. It's polar. It can dissolve into water. And they have a hydrophobic tail, which is water-hating. It's nonpolar. It won't dissolve in water. So essentially what happens is if there's oil around, the hydrophobic tail of a surfactant will embed itself in the oil. And then if you put that into an aqueous environment, into a polar solution, the hydrophilic head will mix in with the water. And in that way, you can get oils to go into a polar solution. So you can see in both of the two extreme pictures how the surfactant positions itself with the tail embedded into the oil and the head on the outside into the water. And in that way, you can get oil and water to mix. Okay. Now, when we think about dissolving, there are three things that affect how fast or how quickly a solute dissolves into a solvent. Most people know these three just through experience with life. Okay. If you increase the surface area of whatever you're dissolving, it will dissolve faster. It's like taking a sugar cube and breaking it up. If you stir it or agitate it, that will increase the rate. And then if you increase the temperature, that will increase the rate. So these are all three things that increase the rate at which a solute will dissolve into a solvent. Now, why do these factors increase the rate? These factors increase the rate because they increase the rate of dissociation and hydration, right? In order to do dissociation and hydration, you need the solute to come in contact with the solvent. So essentially, all three of these steps increase the rate at which water or the solvent comes in contact with the solute. So the more surface area we have, the more the solute is exposed to the solvent, in which case the faster it'll be able to dissolve. When you agitate it, you're continually bringing new solvent into contact with solute, which will also help it dissolve faster. And by increasing the temperature, you're increasing the rate at which the solvent and solute move, so they're more likely to come in contact with one another. Essentially, when we think about dissolving, it's all about the dissociation and hydration. How can I make dissociation and hydration happen better, more quickly, things like that. So in this case, talking about rate, we want them to hit each other more often so that dissociation can happen at a more rapid rate. Now, in terms of how much you can dissolve, there is a maximum amount of solute that can go into any solvent. Okay? Because we need water to both attract the whatever is being put into it, as well as hydrate that substance, eventually we run out of water available to do those actions. And that moment where we run out is called saturated. That's the maximum amount that can be supported given the amount of solvent at any given temperature. Okay, and again, that's based on the dissociation hydration, having water available to do the dissociation and hydration. If we have less than our max amount, that's just called unsaturated, right? We could put more in and still have the water support it. There's something cool that can happen for solutions, and I'll show you guys this on a different day, that's called supersaturated. And essentially what you do is you dissolve your solute into the solvent at a high temperature, and you maximize the saturation at that high temperature. Then you let the solution cool down. And usually for most solutions, as they cool down, they will simply release the crystal that is in there beyond the saturation point for any given temperature. So as it cools, you'll have recrystallization happen. But for certain substances, as it cools down, it actually stays dissolved, in which case you are dissolved beyond the saturation point. Okay? So it'll look like a liquid at a lower temperature, even though you have too much in there. How we do that, again, it's only for certain things, but we have to heat it up and then slowly let it cool down without disturbing it. And that actually holds a lot of energy in with it as it sits there. Those are the main concepts from class if you missed it. So go ahead and have a nice night. Make sure you took some notes on it because you'll need this information as we move forward.